Thank you. Hello. Today we will talk a bit about automotive again, after Martin, of course, and we will discuss about the specific protocol, UDS, or Unified Diagnostic, our methodology, how we will approach it during our pen testing, and how we fuzz it, and how eventually we ended up finding this vulnerability in most of the biggest OEMs that we were testing. Some stuff about me. I'm a senior cybersecurity consultant for Auxilium Cybersecurity by day. By night, I'm an independent security researcher. I want to hack everything, like especially cars. I'm really addicted to Troopers, as you can see. And for more boring stuff from my CV, you can go to crossplace.com. I want to give some props to Niels and Enrico from their talk yesterday. They did some really good introduction to UDS, but let's give also an introduction. This is a high-level overview of many of you from the computer science field and networking. You would know the OSI model, and this is something similar for the automotive sector and the different interfaces that might exist in the different vehicles that we're testing. Basically, we will focus on the application layer, our target, and more specifically to the UDS on CAN, but everything you will learn on this talk, and you can replicate it in all the different interfaces. So we will basically attack it through CAN, but you can, UDS is more or less the same on FlexRate, DOIP, LIN, and all the other interfaces that you might find in a vehicle and can host UDS, or Unified Diagnostics. Let's talk a bit about the message structure of UDS messages. First of all, we have a pair of arbitration IDs. This can be either 11 bits or 29 bits. They are two, one for the server, which is the vehicle, and one for the client, which is usually the tester or the device of the service department that plugs to your OBD to do the diagnostics or communicate with any ECU in your vehicle. Then we have the protocol control info, which states if it's a single frame, if the message that we're sending is a single frame. If it's more than one frames, we state if it's a first frame or a consecutive frame, and we also state the flow control frame when we need to receive more than one messages. But this is more into the ISOTP protocol, and we don't need to spend a lot of time on it. Then the most interesting part, and the one that we will focus on, is the service IDs. So under the UDS, the Unified Diagnostics, you can find a lot of services that you can communicate. With them, you can communicate and perform specific actions. These service IDs, it's only 1 byte. And there are several standard IDs under the ISO, but and the rest of them are just manufacturer-specific, and we have to find them ourselves. Some of the services have also a sub-function byte, and this sub-function byte specifies which exact functionality of the service we need to use in the specific scenario. This is also 1 byte, and there are also several standardized sub-function IDs for each service, and all of the rest are manufacturer-specific that we have to find ourselves. The rest is applicable data to each service, and then we have padding. On our test cases, because we will use a specific tool, we will just use the 0 padding, but you can find many different iterations of that. Let's start focusing on the service ID, because it will be the main topic that we will see today. And as you can see in UDS services, in a specific service, you will have a specific request SID with the corresponding response ID, service ID. So for example, here you can see that in one of I have some examples of services. One of it is the diagnostic session control, for example, when you need to send this 10 byte as a service ID in order to request a change in the session that you are into in the specific ECU that you are targeting, and the response will be a 50. So you should expect a different byte from your request. Next, we have the negative responses. So as you see, we have the same services, but the response will be always a 7F. So if you receive a 7F, then you should look at the sub-function ID, so the sub-function ID of the negative response, or else a negative response code. And this will help us enumerate further the ECU and find out why we get a negative response. Is it actually a service? Is it not? Why is it rejecting us? Is the service supported? Is the sub-function supported or not? So this will help us better enumerate the ECU and find out why this service is responding with a negative response. Next, let's see about some of the requirements that we will need, because in order to test an ECU with UDS, you will need some prerequisites. Of course, you need to have a vehicle, a way to interface with the device, and some software. We have the vehicle, let's assume that we have it. The way to interface with the device, usually we try to use some tools that are widely adopted, they have a good community, they're supported by the Linux kernel, and we can communicate with them in an unobstructed way. The tools that we usually use, basically, we're not developers, we are basing our development and research on Python, which is easy and fast to develop something. There are some libraries that you can use, like ISOTP, Python CAN tools, and some widely adopted tools on the industry. Scapy, that there was a talk yesterday for this specific part of Scapy, the automotive one. CanUtils, Karin Caribou, which will be the one that we will talk today, and CanMap. Karin Caribou is basically a security testing tool for automotive. The good thing is that it's modular, so you can just develop your module, pass it, pull it to the GitHub repo, and the community will make the changes, and they will accept it or not. There is zero knowledge needed, so you just plug your CAN adapter to your vehicle, and you can start enumerating and fuzzing. This is the help page, for example. You can see the different modules that exist. There is the DOIP module, a UDS fuzz, which is the one that we developed. Also, the DOIP, we developed it. There is a fuzzer module, and many more in order to communicate with an ECU. But let's start fuzzing. This is why you are here. What is fuzzing, first of all? It's the supply of expected or unexpected behavior. We analyze the result, and that way we understand the target, and we monitor for unexpected behavior. So basically, we can find unexpected behavior in many places, and believe me, in this talk, you will see that we can find it in the most unexpected places. Let's start with the arbitrary ID enumeration. First of all, we have to find which are the target IDs on the specific bus that we are connected, because every ECU has a different pair of IDs. We have to see if they are 11-bit or 29-bit, and if they are standardized IDs under the ISO or manufacturer-specific. For the arbitrary ID enumeration, basically we are iterating through all the arbitrary IDs. This is an example of the 11-bit arbitrary IDs that goes from 0 to 7FF in hexadecimal format. Of course, we send basically a diagnostic session control for default session, because usually, mainly in all of the ECUs that we tested, you have to find the default session on this ECU, and we're iterating through all the different available points to find out if we get a positive or negative response after its iteration, and we resend the request to prove the existence of server and client IDs. To see it in practice, I have a demo here. You can see we're using the Karin Caribou UDS discovery module, so that way we can discover on this specific interface and the specific buzzword that we are connected, how many IDs that we can find, so how many ECUs. This is on a vehicle, and all the tests are in a vehicle of 2022. I will not reveal the manufacturer, but it's real-life test cases on real vehicles that we found on the wild. And as you can see, in a couple of seconds, we have the results. We have the client IDs with the corresponding server IDs. This means that we have different ECUs, and we can communicate with them by sending from the client ID messages to the server ID that they can be accepted. So yeah, here you can see client IDs, corresponding server IDs, In order to communicate, you just communicate through these two IDs and expect the messages back. Yep. Here, for example, is a specific ECU with these specific IDs. We are connected to the OBD port of the vehicle, not something extreme and custom connection through specific buses, but just an OBD device connected to the OBD port under the steering wheel of the vehicle. And here you can see the difference in the different results that we have. Here you can see a positive response from an ECU. In the first column, you have the interface, CAN 0 in this example. In the second ECU, from the enumeration you can see that it sends a 1001 in all the messages, 1001, so default session on the change session request. And you can see that some of them, of course, are responding with the 5001, and some of them are responding with the 7F. So then you have to replicate your results and see slowly which ECU was responding in order to have the appropriate results in the end and not have false positives. Something similar is the service ID enumeration. It's really similar. It's way simpler and way faster because it's only 1 byte long. Each ECU has different sets of services, and you get an immediate response for existing services, of course. The UDS request here is similar. You just supply now, because you already know the different arbitrary IDs. You specify those arbitrary IDs to the tool, and you iterate through the different services from 0 to 7F, and you monitor for positive or negative responses, with the result being the list of the available services. Here we have another simple demo, really fast. You can see iterating through all the possible services. And here we can see a really well-defined ECU with no proprietary and not manufacturer-specific services. All of them are defined by the ISO, which is also something that it's included in Caribou, and you can, if the service is mentioned in the ISO, you will find it also here. We will use some of the services later in order to fuzz and use the rest of the attacking points. And similarly, we can also enumerate the sum function byte, but it's a bit tricky. There are several different diagnostic sessions, and sub-functions may only exist under this specific session or ECU modes. For example, you can switch to a bootloader mode where only specific sub-services will only exist on this mode, so you have to thoroughly test it and find all the possible outcomes that you can find in this ECU. Negative responses can also help us clear things out a bit, and that's why I said that it's a useful tool to enumerate and find more information about the ECU. So now that we have a basic understanding of the UDS and how it works and how all the services are laid down, let's check some fascinating and dangerous use cases that we had throughout our pen tests, what we found, and how we managed to exploit those issues with really simple, to be honest, attacking methodologies. There are several security and safety critical ECUs in the vehicles. We have to keep that in mind, and usually there are no applicable preconditions on those ECUs in order to execute some functions that can result in not only security issues, but also safety issues. One of these examples is the ECU reset, which does, as it says, like it resets an ECU in different ways, which can directly affect the safety critical components, security critical components, and even the functionality of other ECUs on other buses of the vehicle that are interconnected. The sub-functions of ECU reset can be a hard reset, key on-off reset, soft reset, and enable or disable rapid power shutdown, but there can be also some manufacturer-specific sub-functions, as discussed before, that you have to enumerate through them and see, depending on the reaction of the vehicle or the negative responses, what you can do with them. Here it's an example from the same vehicle. This is not an injection of messages into the CAN bus that presents this message, as Martin said, from 2011. It's something, we basically reset an ECU and it never gets up until a complete power cycle. And this means that depending on the criticality of the safety of this ECU, it will have the appropriate result. So if this ECU is the battery management system, you might cut off from the whole battery of the electric vehicle, or if it's the steering ECU, you might lose the control of an electric steering ECU, which, of course, you can understand it's dangerous, and throughout our pen test, we found also that there were no requirements on the speed of the vehicle on many of our assessments. This is another example. You can see here that the blind spot light, the blind spot LED, it's blinking when you reset it. So you can imagine some scenario when a user is really used to this blind spot, that it works properly, but after some point, after like a couple of years that he is used to it, you can potentially target him and make a really specific scenario that you can drive him to another vehicle in a targeted thing. Yeah. Another scenario can be write data by identifier and read data by identifier. So there are some predefined memory locations in its ECU that are managed by the UDS protocol. They are 2 byte-sized addresses, and usually they host vehicle information that you can find, like the VIN, like some information, the mileage and other, we will see later. And size has to be specified and fixed by the manufacturer. Here we request data parameters. The request data parameters are parsed by the host ECU, as you can understand. So the data that we send or we request are parsed and have to be parsed by the ECU. And so, as you can understand, supplying unexpected amount and type of data can potentially result in crashes and memory overflows. And we saw that in the wild. It's really difficult to exploit it properly. But because we had the ability to plug a debugger, a proper debugger from the manufacturers, we saw that it was actually concerning, and we could find the memory overflows on these ECUs. Maybe someone more focused on it can potentially exploit it further. Is this the game over that we discussed? Not yet. Let's see some juicy stuff that can be found inside the data identifiers. First of all, we found secret keys, we found passwords, we found mileage. Just guess, and commands that can get executed in the underlying OS. Yes, many times you have Linux systems, Android systems, especially on the VHUs, so the head units, which are also ECUs. And if you find on the data identifiers some commands, maybe you have to enumerate it further, because here we have an example from a thesis we did with a university, with one of our interns, and it's directly replicating results from a client because we could not reveal actually the results from these pen tests. But let me focus on that. First of all, on the first column of the result, you can see that this is the identifier, as I said, 2 byte identifiers. And then you have the hexadecimal data that you receive from the ECU. If we turn this hexadecimal data to like ASCII, you can see that it's a command. It was a software update command. In this case, it's a PI that replicates this vulnerability. And what we can do with it, we can write to this identifier. If there is no prerequisite for a security access to write to this identifier, you can write your own command or pipe a new command and then get code execution from the Wi-Fi access point of the VHU or from any other connections like Broadreach, FlexRay, or any other connections that you can get a network connection to the specific ECU. Noteworthy services that you might be interested in following up and doing your own research is communication control, write memory by address, so you can find also memory addresses inside the ECUs that you can write and read from with UDS, routing control, and request upload. And then, for the main part of the talk and the service that we will approach and attack is the UDS security access. This is the main solution to restrict UDS functions under a security mechanism. So you have this security mechanism which is algorithmically secure, and it has different levels of security access, and manufacturers hide, let's say, different functionality under this security access. It's a seed key algorithm implemented and obscured by the manufacturer. So the way that the key is derived from the seed should not be revealed, and usually there are some leaks online, or there are some seeds that get leaked, or algorithms, or some people reverse those algorithms in order to get access to these ECUs. This is a representation of how the UDS security access works. So we have the client and the ECU. Those two have to communicate through the arbitrary IDs. First of all, the client sends a seed request to the ECU. The client can be either you as an attacker or the service department devices that usually are available when you go for service to fix your ECU or to update it or anything. After the seed request, the ECU generates a random seed and calculates the key out of it with the predefined algorithm from the manufacturer. The random seed is sent to the client, and the client has to also calculate the key and send the calculated key to the ECU. So you can understand that the client has to know this algorithm in order to make this pairing between the two different ECUs, and eventually the ECU verify the key and grant access to the client. Here I have an example, and keep this example in your mind. It's requesting seeds to a specific ECU in the vehicle that we targeted before. And I want you to keep it in mind, because later we will basically do the same, and you will see the difference in results. As you can see here, we are requesting like a lot of seeds. Every line is a seed, and it can be considered a really secure seed because it's long. It cannot be brute forced easily. Like, it will take years or millions of years to brute force this seed and get security access. And there are also mechanisms to block you from sending calculated keys again and again. So you can be easily blocked by that. Here you can see some in more detail. First of all, we have diagnostic session control. So we change the session from the default session, which is the default session of the ECU, the default state. We get a positive response with 5003. Now we are already in the extended diagnostic session. And after that, we request a seed with the service ID 27 and 01, because it's the 01 security access that we are trying to get on. Then you have a 10, because we are specifying that this is a bigger message than it can fit on a single message. And then we have the flow control message in order to receive more than one messages, and construct the whole seed in order to parse it, analyze it, calculate the key out of it, and send it back to get security access. Common attacks in this service can be pre-calculated key fuzzing, as we discussed, and brute forcing, which is not directly applicable in seeds like this, but we also saw 2-byte seeds that can be easily brute forced. Fault injection, fallback function triggers, and algorithm reverse engineering, which is the basis for leaks, where you can find for many vehicles online to use and understand how these algorithms work. But what randomness means either way, and is this process really random? What if we, and I will pass this to you, what if we could request the same seed more than once? This is what we're trying to approach today. And we need to also mention that this is a really common issue in the embedded world due to the limited resources of all these devices. So when you have so limited resources, your source of randomness usually is not the most advanced. This is where Sekar comes to this game, and he developed, basically, he started his research as a PhD, and he released his research as revisiting remote attack kill chains. And the candidate vulnerability is the one that we are targeting in order to request the same seed more than once because of low seed entropy. And this is a really interesting research. It's more than the candidate vulnerability. It's a whole kill chain. If you're interested, just go to it. Basically, what we analyzed and what we found is that most of the ECUs that we tested has randomness based on the processor uptime. And the processor uptime resets during boot, which is an issue, and it's a weak source of randomness. Most of the industry is affected. Like, we worked with a lot of OEMs and tier 1 suppliers, and we found out that like almost 90% of the ECUs that we tested had this vulnerability. And this, of course, states our previous example as like vulnerable. The seed is not random, so if the seed can be guessed, we can also pre-calculate the key and get, or if we own a pre-calculated key, we can grant access, have access to the security access of the UDS. But let's find that seed. We started by developing custom scripts for Python and C. Customization for its target ECU was needed, so it wasn't so good that we customized our tools for every ECU, and we needed to automate it somehow to start gathering more data and faster testing during our assessments. This is an explanation of our attack, because basically in the research there was no explanation of the attack. It was just a theoretical representation and how they ended up on these results. But here I will explain how we will approach it. First of all, we issue an ECU reset to the target ECU. The ECU reboots. Of course, this has as a prerequisite that the ECU reset is unrestricted under security access. We have to have access to the ECU reset in order to do it. And usually, we need a hard ECU reset because this will reset the processor uptime. The ECU reboots, and then we wait for a predefined amount of time before we issue a seed request to the ECU. We receive the seed. If the desired seed is not the one that we want, we go again and we reiterate through the steps. But if the seed is the one that we need, we send the pre-calculated key that we already own as attackers, and we grant security access. This is the module that we developed. It's under the car in Caribou. It's already available. You can download it and play with your car. Please be careful. Don't drive and while testing, and don't break anything. They will not fix it. There are two sub-modules. It's the delay fuzzer and the seed randomness fuzzer. It seemed like the proper target, basically, because first of all, we're not developers. Secondly, it's open source. It's modular. They were really helpful. They helped us fix some of the issues in the implementation, and we implemented it both for CAN and DOIP implementations of the UDS. First of all, we have the seed randomness fuzzer, and this is the tool to evaluate an ECU if it's actually vulnerable or not to this vulnerability to weak seed randomness. And if you remember the last thing I told you about this, the seed requests that we saw, here we have the evaluation of it with our tool. And you can see something strange, that every seed is the same. This is an extreme scenario. It's actually an actual ECU from an actual vehicle that we had, and we are connected to the OBD port. And why this happens is that every time we reset it, we get this predefined delay between the ECU reset and the seed request, which in this case is 1.102. And because the change in seeds, like the iteration of the seeds, is really slow, so it happens every 1 second or something, we can actively find the same seed every time we reset the ECU. The thing is that in real-world scenarios, in other real-world scenarios that we had, we didn't manage to get so many same duplicates, but you can see in the end that we state the duplicates that were found, because in the analysis from Sekar, he found out that if 20% of the seeds that you receive from the 1,000 seeds in total are duplicates, then you are pretty sure that the ECU is vulnerable to this, to weak seed randomness. Here we have the example. Yes, as you see, all the seeds are the same. Because this ECU was really vulnerable, and it states as the duplicate in the end. This is an example from the dump that we have at the same time. You can see that we send an ECU reset, which is the 11 service, and 01 is the hard ECU reset. We get a positive response. If you get a negative response, then you have to find out why is it negative and enumerate it further in case it needs some specific security access or some different diagnostic session in order to execute it. Then we get into the diagnostic session, the extended diagnostic session, and then we start requesting the seeds. We iterate through it. It's proposed to do it, to replicate it 1,000 times, as I said. And if you found 20% that is duplicate, then you can rest assured that it's vulnerable. Yeah, this is, as I said, like we discussed about this, but mainly the point that I need to stress is that, first of all, you need an accurate microcontroller in order to communicate and get accurate results. And secondly, you will need some kind of more accurate language. As discussed with Niels before, Python has not some so accurate delays, so you will need to port it somehow otherwise. But for general enumeration and general evaluation of an ECU for this aspect, we found out that it's pretty okay for our pen test assessments. And now, about our second tool, we have the delay fuzzer. And we asked ourselves, what if we already have a seed and pre-calculated key pair? What happens next? And these seed and pre-calculated keys can be, as discussed, leaked through forums. It can be calculated by someone that have security to access to the security access mechanism, and again, leaked somewhere, or by tampering ECUs to the service departments and intercepting those seeds, those single pairs, in order to then inject them and gain security access mechanism, security access, if the ECU is vulnerable to this. And this tool helps us find the delay which is needed between the ECU reset and the seed request in order to get security access with the seed that we already own. So basically, we fuzz the delay until we find the successful match for this specific seed that we own, the pre-calculated key. This is the tool with the different options. We have the session type. We have the target, which is the seed that we own the pre-calculated key, and the source and destination, arbitrary IDs, and demo time. As you see, we iterate through different seeds. We request seeds. These are, again, different seeds because it's we change the delay between the ECU reset and the seed request. And as you can see, we receive different seeds. But in the end, at some point, we found out that the seed that we predefined on our tool, that we specified on our tool, was found with a specific delay that we can potentially use for a POC to get security access every time. So this tool is basically to evaluate and find the delay that is needed between this ECU reset and the seed request, find the delay, and create a POC out of it in order to further enumerate the device after having a security access with the single predefined key and seed pair that you obtained somehow. And this is our game over. This is how we tested all the ECUs. Mainly, sometimes we just ask for a single seed and predefined key in order to prove to them that we can gain security access with a single leak that can happen to the industry. Here it's an explanation of the tool again. Like you can see that we specify our module, the UDS fuzz, and the sub-module, which is the delay fuzzer. Here we specify, and this is a really junky way, let's say, to specify the different sessions, but because of the the manufacturer-specific implementations, the normal coverage of Karin Caribou didn't help us, so we had to find another way to specify the different sessions and seed requests that can be found on an ECU. So after enumerating, you are specifying the different bytes that you want to be executed on the canvas. So here we have 10.03 for diagnostic session control to the extended diagnostic session, and 27.01 for the seed request for the security access. Here we have the seed that we can potentially have a seed and pre-calculated key pair already obtained from some leak or from some enumeration that we did. And here we have the result. After receiving a lot of seeds and by iterating through the delays, we saw that in this specific delay, our predefined seed that we supplied to the options was found, and this means that the target seed was found with this delay, and we can use it in our POC. So we basically don't need to calculate the key. This thing just goes away. We don't have any randomness, and we just attacked this device and gained complete security access that we can basically rewrite firmwares. We can have further access to the unit. We can tamper the device, which means that you can also tamper the network, the buses, the different buses that exist inside the vehicle. And of course, you can understand that it's really dangerous when we're discussing about safety-critical ECUs. The pre-calculated key interception can happen in many ways. As discussed, it can be by weak links in the supply chain. Server shops are the main targets of tampered ECUs. Malicious ECUs can also be used to leak pre-calculated keys. And of course, online sources and forums that might have somehow obtained these keys. Mitigations. Because we also, as pen testers, we always have to supply a mitigation strategy and supply our proposal on how to mitigate those issues. Basically, almost always we suggest that there has to be an HSM, and it starts to appear on embedded devices and specifically ECUs. On the latest models, many times we found that. But the thing is that several modes are still affected, and usually we saw that even by not being able to bypass on the normal mode of the ECU, if we manage to get into the bootloader mode, which is not something really difficult in most of the cases, but you need to find out by reversing or by further enumerating the device on how to get into this bootloader mode, you can potentially also bypass this security access because the implementation, the HSM is only used on the normal mode and not in the bootloader mode. This was also a real pen test finding, and yeah, it's basically a way to bypass the mitigation that they applied. So they have to start implementing it also in other modes of the ECUs. And yeah, of course, I don't have to mention it, random seeds have to always use a proper source of randomness because otherwise they are not random. Yeah, this went too fast. I just have to say that, like, from our experience in the automotive sector, we saw that many companies don't care, and that's a really bad thing to do, especially when we're discussing about safety-critical components, safety-critical devices. And this is our job. That's why we are here. We as pen testers, as researchers, and everyone here has to pass this culture and start discussing about safety-critical components and safety-critical findings that can potentially affect the industry in a different way. Okay, these things might not affect some normal device. You might not care about the leak of your private key if you're not private savvy or something else. But in these vehicles, the culture has to change, and we are the ones that will do this change. So we'll start this change, yes. So thank you for your attention. Please hack cars, make love, not war. And yeah, see you next time.
Hi, thanks for the nice talk and the very inspiring last words. Do we have any questions from the audience? Yes.
Thank you. At first, thank you for your nice talk and also the layout for your, from your slides. I have a question on the authentication method. Do you see that there is a change in the way the authentication happens? Like the CDK is not enough, that we need real crypto also?
Usually, it depends on the implementation of the algorithm from what we saw. So there are more secure algorithms and less secure. Also, there are in many cases, we found fallback algorithms that you can potentially trigger through some function, and they're way less secure. So I can see it as a good enough way to secure the vehicle, but you have to implement it properly. You have to implement the proper crypto. And now there are different services that they're used. You have also private keys in the game, but you can understand that you have to also implement it correctly. You have to have some HSM to store your keys. You have to find a way to update the keys if they get leaked, or if your certificate authority gets tampered. So it's all about the implementation in the end. Yeah. And the security access algorithm might be enough, but we have other ways to secure it. Yeah.
Okay, thank you very much.
You're welcome.
Any other questions?
So in your first attack, when you were able to get one particular seed, derived from that, how would you get the particular key? Because I understand the second example where you have already a seed and key pair, and then you are having a particular delay. But what I didn't get, at least not from the talk, is if you have just the seed without having the algorithm. Because if you have the algorithm, then you do not need to do this. Then you can just generate the particular key. So more like, I think you got the question.
Yeah, I got it. So basically, there are two different tools. The first one is to evaluate the seed randomness of the device. Basically, it's not a continuation of the attack. The second tool is not a continuation of the attack. With the first one, you run it in order to see if you can find duplicate seeds. So as I said, the default is to run it 1,000 times, receive 1,000 seeds, and from that, if you have 20%, which is duplicates, then you can consider your ECU vulnerable, and you can start searching further to see if you can find a seed key pair that you can use for the delay hazard afterwards and get security access. So it's not a way to find a pre-calculated key, it's a way to evaluate if your ECU is vulnerable with the first tool. And with the second tool, if you already have the pair, then you start fuzzing with your seed to see the delay in which this seed appears, then build your POC and get security access. Thank you. No.
Anyone else? We do have quite a few minutes left.
So after you gain security access, do you usually go farther?
Excuse me, I cannot hear you.
Okay. After you got the security access, do you usually go farther? Do you also do further exploitation steps once you have security access on an ECU?
I didn't get it. Like when I get
okay. Once you have security access, what are other things you could do afterwards? Is there any other things you do in your usual pen tests to show the criticality of security access?
Yes. So basically, we try to approach the services that are only approachable from the security access. This can be upload of data, right to specific addresses, right by identifiers that might be restricted under security access. So you try to find things that are only accessible through the security access. Basically, the main target is completely rewrite of the firmware. So we request or dump the firmware in order to get it, tamper it, then upload to it, and possibly play with the algorithm or get something inside the data identifiers and prove that we can completely rewrite the firmware with this security access. If it doesn't allow us, we have to find other services that are accessible through this security access that is vulnerable in order to prove it. Yeah. But usually it's tampering with data inside the ECU, that you can only do it through security access and might be really critical. So for example, you might have temperature thresholds for battery management systems that this can create huge deals like, not explosions, but it can completely destroy the batteries on electric vehicles after a specific temperature that is only hard-coded into the ECU. Other examples might be change of the broadcasting through the OBC connector in electric vehicles, so that way you can connect to a malicious charger really easily and get access to it through this interface. And yeah, basically it's changing of the memory, like altering of the memory and tampering with it.
How many different levels of security access have you encountered? Like, is that a binary thing, secure and insecure, or?
No, usually there are more than one in a single ECU. And not only a single one, but as Niels and Enrico discussed yesterday, it's really difficult to find out the specific path to go through it and get the security seed, for example, in specific ECUs. So the thing is that not only more than one security access mechanism exists in a single ECU, but it's also a bit tricky to get into them in many cases. Getting to them then gives you different functionality. So there might be a simple security access and a programming security access where you can only rewrite firmware on the programming security access. So you have to further enumerate when you get the security access to see what are your possibilities and what you can do after it.
I think you only quickly mentioned about possible memory corruption attacks that you could find with fuzzing. Did you explore this? And if not, why not?
We didn't exploit it. Basically, like, there was a similar discussion yesterday. We are not doing security research, we are doing pen tests. I'm doing the security research on the side. And the thing with pen tests is that you have limited time. Usually these devices have different architectures. We can be supplied by the manufacturer with a debugger that we can use to see that the actual memory is overflown or some memory corruption is happening. But in order to exploit it properly, it takes too much time, and I don't know any real-life scenarios where someone managed to actually exploit it. I can see it happening more in Linux-based systems with ARM processor, for example, which is more well-documented, and it would be easier to do. Because UDS also exists in the, as I said, in the vehicle head units, which run more commonly used architectures and systems.
But the tool you developed, this fuzzer, it could be used to find such things.
No, you can actually fuzz. Like you can even fuzz it with, you can fuzz this pre-specified space, for example, in data identifiers by doing some specific configuration in the fuzzer module of Karin Caribou. But the thing is that even when you overflow it, you have to spend significant amount of times to exploit it properly, to build a POC in order to get something out of it. Memory corruption doesn't directly give you something. It's just a finding that you know it exists. If you don't exploit it, it's not as severe. Or if you don't agree with that, yeah, please let me know.
No, thanks.
Yeah, that's how we rate our findings, basically. Yeah. Okay. Thank you. I think that's all.
I have.
Okay.
No, you go first.
Yeah, I have a question. Did you try, or do you know that, because on the list on how you can get seed and key pairs, I think as CAN is a bus, for example, you could easily use your regular car, build in a sniffer on the CAN bus, like a passive one, drive to your workshop and have a maintenance, and then they use their diagnostic devices, and then you can later more or less analyze all of the stuff that was going on the CAN bus, and I'm pretty sure you'll find some seed and key pairs. Yeah. Yeah,
that's true. That's the main target. Basically, you have to target the network inside, the different buses that are interconnected. Usually, I don't think that you can easily do it from the OBD, but tampering the different interconnections between the ECUs would be pretty straightforward. And you can do it like put your car into the service department and just listen to all the buses to see what you got out of it. Yeah.
Actually did something like that just for the
Okay, cool. I think you had one.
Yeah, maybe a bit different, weird kind of question, but I was wondering, in your penetration testing work, do you somehow develop a feeling for which types of ECUs are usually more vulnerable than others? So if you have to test a specific type of ECU, do you sometimes know beforehand that it's going to be vulnerable just because of the type of ECU it is?
Yeah, I will just say that it's usually depending on the manufacturer and not the type of the ECU. Yeah, we have some idea beforehand when we do the full vehicle penetration test, for example, because it's like you have different ECUs from different tier 1 suppliers. So we have an idea that this ECU might be vulnerable to that, so this is a lead to move towards this path of exploitation. But the thing is that if you're doing a penetration test, you have to cover some methodology, something like what we described today for this specific protocol, and you have to cover the whole thing in order to be able to say that this is secure or not. You cannot just skip stuff. So even while knowing, this is just a lead to go faster through this vulnerability and see if it's vulnerable or not in the end. Cool. Thank you for your questions. I appreciate it.
All right, then thanks again, and let's thank the speaker again.
Thank you.